Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy in my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Denys Bondar. He's an assistant professor at Tulane University in the School of Science and Engineering. And we're going to talk about quantum technology and what are called ultra-fast nonlinear optics. So, Denys, thanks for coming.
Thank you very much for hosting on this wonderful podcast.
Thank you. Well, tell me about your research. What does it do? What are you working on?
So I actually work on different directions, just to keep myself not bored. But my main thrust at the moment is trying to revive the dreams of alchemists. So can we rethink alchemistry from the point of view of quantum technology? So as we know, alchemists, of course, in the popular culture, they're scorned, they're like laughed at a bit. But in reality, I think their legacy is quite important. If you try to use a modern language, they were data scientists. They were collecting enormous amount of data on how substances interact. They were actually, first of all, they were scientists in the basic sense of this word. And they're famous for trying to achieve transmutation of lead into gold, among other metaphysical tasks, right? So as we know, in 20th century, a new branch of physics started. It's called nuclear physics. And in fact, it turned out that this is possible. This is possible to turn lead into gold through a rather complicated chain of nuclear reactions. This is doable. Obviously, this is not something that we would like to use this has no commercial value. This is just way too expensive to be of any use. But some of the heavy elements are actually obtained in such a way of practical importance, for which this is economically makes sense.
Oh, so you mean there's some commercial efforts to make man-made elements that exist in nature, or that ones that literally don't exist in nature, like transuranic ones?
Of course, exactly. This is a very important field of research. And this is, in fact, how even, I apologize not to remember exact date, but several years ago, maybe 4 years ago, 2 new elements were added, right, to the periodic table. It's precisely that, these attempts are still being made, and, it's a fundamental case. But moreover, as a, expert in life sciences, that, radioactive elements are also used for cancer treatment, and some of them are synthesized in special like nuclear labs, right, near power stations. So this is useful for something, but not for making lead to gold, this particular idea. So it already, this fact already sort of makes alchemists, mainstream, Now, when I was several years ago, we were working on a different project using quantum technologies. And then we realized that what we are actually working on is basically alchemy in the new light. What do I mean by this? So when we when we as we just presented, that we can actually turn actually lead into gold. It's possible to do via nuclear physics, nuclear chain of reactions. But what if you are asking a different question? What about making lead look like? So the key is look, not be gold. And this sounds maybe a little bit very close, but in fact, those are very different questions, because the question about making something look like something else is related to optics, the science of light. So suddenly, by formulating this question this way, you talk about optic, problem in optics. And we thought about, so what will it take for one element to look like another? So to understand, I will just give the punchline. It is actually possible. It is possible. And let's just understand what does it take to make this work. The idea is, why do we see things? We see things because light comes in, interacts with this substance, and transmits or reflects back and comes to our eye. So we see this difference between light, that incident light, and the outgoing. Or in more scientific terms, there is a difference between optical input and optical out. So how is this optical input is related to optical out? So in other words, we try to ask ourselves the question, and maybe it's a bit silly, but we try to think, so optics is a really old, ancient, science, not like nuclear physics. It's really ancient. It's as old as Newton's mechanics, right? If not, to be honest, it's older than that, but more modern, started from Newton. And we decided, let's just treat this as a black box sort of engineering problem. So what is the properties of input connecting to output? What are the properties? So, it depends on light. It depends what kind of light you use. So, for example, if you use an everyday light, weak light, such that, we use light bulbs, son of light, and it's a weak light. So it's all weak, and it's known that the relationship between optical output and optical input is simply linear, right? So, if you put twice as much light in the input, you get twice as much on output. So linear relationship automatically implies unique relationship between input and output for a given substance. And that's actually what I said is a little bit maybe abstract, but what I said is that it's a fundamental thing.
So what does that mean? If you hit an object with photons of a certain frequency, you know what's going to happen, but in these substances you don't? What do you mean?
So what is it? Giving any substance, as long as the light is weak, the relationship between input and output is unique. And this is how we know what stars are made of. This is what's called spectroscopy, right? This is used in life sciences, in astronomy, in industry, to detect, to discriminate, to identify substances, right? The compositions. It's precisely because when you shine a light of certain frequencies and you measure what comes out, you can work out what happened in between, and that tells you what the material is made of. That tells you there's a unique relationship between input and output for a given substance. And again, this is a really, really important tool, right? Literally in every aspect of technology and science. And that's great. That's amazing, right? That's absolutely fantastic. It's one of those miracles, to be honest, that we don't notice, right, anymore. It's like so boring that nobody talks about it, but this is pretty amazing. 100 years ago, right, a little bit more than 100 years ago, actually, people were just dreaming about this, right? They were saying, we would never know what stars are made of. Only 150 years ago, this was like common point of view. We would never know what stars are made of. But now we know everything. So now, what happens if you use a bright light? And what do I mean by bright light? That's like light of laser. That requires a laser. So if your incident light is bright, means you have a laser, then the output and input no longer have a linear relationship. And this is very interesting.
What are the reasons? Because you're breaking bonds in the substance, the target, or what's the reason?
The reason is that biologists, physicists, and mathematicians are asked to make predictions for horse race. And so biologists start, I need to, in order to predict outcome of horse race, I need to know the diet, the exercise schedule, the well-being, the medical history of horses. So they ask, mathematicians, here in this sense, I meant statistician. What do you need to predict? I need to know like odds, previous history of winning, success, what weather pattern to predict. And then they ask physicists, so what do you need to, let us assume that the horse is a spherical ball moving in a vacuum. So what happens is that, molecules in this joke, right? We visualize molecules as sort of like a harmonic oscillators, right? Like a pendulum. And if you don't excite pendulum, right? If you don't excite pendulum too hard, I have a daughter, 2-year-old daughter. So I take her to swing. So when I push a swing, which is pendulum, it doesn't matter how hard I push, the frequency of oscillations or the period of oscillation swing does not depend on my strength, basically the way I push it, right? It's just determined by her mass and the length of the swing. So, and that's true as long as you don't start, doing child abuse and pushing really hard, like so that swing will go like almost like 90 degrees.
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
And the reason is that actually the swing no longer behaves like as a simple harmonic force, right? It becomes a nonlinear system. So the same thing with molecules. If you start pushing them too hard, if you start moving electrons, in this case, more specifically, we mean electrons, you start deforming electronic clouds in atoms or molecules too significantly, it starts behaving like a sticky jelly, and it's no longer simple like a rubber band, right? So you deform slightly and it restores back to normal. Deform slightly, restores back to normal. Deform slightly more, it still restores back to normal. But you start deforming them hard, you start feeling it's like a jelly. So it has some viscosity, some dynamics. And it's precisely, this, shall we say, non-elasticity of dynamics of the electrons in atoms and molecules.
So you're trying to do modeling of what happens in these nonlinear ranges?
Yes, it's not only us, it's a mainstream research. It's like a large area of research called nonlinear optics. Exactly, that's of interest. And I should mention that historically, this field was actually, interesting enough, it was started by a woman. She was the second recipient of Nobel Prize in Physics, but for nuclear physics. And she actually, in her PhD thesis, she predicted, actually I forgot her name, she predicted the existence of that this is possible. Actually, before her, nobody thought this is even possible. She saw theoretically it's possible. And of course, this field became officially nonlinear optics started as a research in 60s once lasers were discovered. Okay. So this is a very, scientifically speaking.
Is it Donna Theo Strickland?
Oh, no, she's the third woman. 1 second, I'm going to find her. Yeah, Donna Strickland, actually, by the way, she's also Nobel Prize, her discovery. She was actually on my PhD committee. Her discovery actually took nonlinear optics to absolutely new heights because she learned how to produce really bright laser, like really bright radiation. So actually, as you can see, 2 Nobel Prize winner actually played an instrumental role in nonlinear optics. So Maria Gopper-Mayer, that's the name of the second woman to receive Nobel Prize in Physics, and Donald Strickland was the third one recently in 2018. So Maria Gopper-Mayer received the Nobel Prize in 1963 for nuclear physics, and not for this foundational work, theoretical work on nonlinear optics. As any genius, right? Usually they make more than one discovery, really important discovery.
So what's the point of driving these substances so hard? Like, why is it important to be able to drive them harder? Is there a commercial use for this, or what's the point?
It's very important. So if you start driving, so spectroscopy, as we discussed before, based on this simple linear relationship between input out. Unfortunately, as substances become more complicated, we talk about molecules bigger and bigger, and especially this is a very big problem in life sciences. These fluorescence markers, for example, they have a really similar optical absorption and emission spectra. So their signatures, linear signatures, spectroscopic signatures are very similar. And of course, if you have the substances which have similar, which look similar, right? It's hard to discriminate between them. And what happens is that once you use nonlinear effects, when you try to drive them nonlinear, actually, even though they could look very similar linearly, when you start to hit them hard, they actually look quite different. And so this is the purpose of precisely the area of nonlinear spectroscopy. It's spectroscopy based on driving molecules, hard optically. Okay. And it gives you better sensitivity, better selectivity, better accuracy in detection and discrimination. it's of commercial use. It's sort of use in industry as well as science and technology. Now, however, because you need to drive them harder and harder, right? So this requires lasers. So usually this is more costly as far as equipment goes, significantly more costly than linear, than regular spectroscopy.
Okay.
But nevertheless, it's important. It's an important area of research, right? In application.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
So going back to the question about alchemy. So once you have lasers, as I just to reiterate, once you have lasers, there is input and output are no longer linear, therefore they're not unique. It's like if you allow myself to use mathematics here a little bit, if I give you a quadratic equation, right, and ask you to find how many solutions are there for a quadratic equation, for an equation which has a second power, there are two. In principle, there are two solutions, so it's no longer unique. But if you have a linear equation, you have only one solution, a single solution. So the same thing is in linear optics, right? There is one unique relationship between input and output, and there are multiple relationships between input and outputs when you drive them nonlinearly. By the way, that mathematical argument is actually, it's quite close to reality, to rigorous argument. I hope it made sense.
What kind of applications would this be useful for? What benefit do you get from driving a substance, harder than you normally would linearly?
Yeah. So let me first maybe a little bit
model, but
if I may, let me just complete this explanation how we make lead look like gold. Just one sentence, and then I will go to this answering this question. So once you have non-uniqueness, you can ask a question. If I have a non-uniqueness, then can I make lead look something else, right? Because if lead is not looking like lead, you can make it look something else. Non-uniqueness means the same substance can look differently depending on how you shine light. And the answer turns out positive. It turns out to be under very reasonable physical assumptions. Turns out to be a universal possibility that yes, for any given substance and any desired optical output, we can find a laser pulse that will induce the optical response from a given substance such that it looks anything you want. So this is a possibility. And
when you say nonlinear optics, does that mean that the substances will be used to transmit information along fiber optic cables, or is that just a generic name for what you're doing?
Yeah, it's a generic name, but optics means light, basically, right? Science of light. Okay. Yeah, so of course, for a general audience, optics is usually associated with fiber, but optics means literally anything that involves light, scientifically. And it could involve fibers as well. It could be any context, right? It's what I'm describing. But what's valuable here is this universality. For any given substance, we can always find a laser pulse that will make this substance look like anything you want. But there is a catch. Only for the duration. This is guaranteed to be only for the duration of the laser. As long as the laser is on. Once the laser is off, all bets are off, and most likely it will just, return to its normal state as it was before. So in this way, right, unlike nuclear physics, right, where you actually literally change substance, right, lead to gold, for example, physically you change it. As a nucleus, you change nucleus, right? You change the number of protons, the number of electrons. Here, it's only transient behavior, right? It's only transiently while a flashlight is on. And this is, this discovery there's a number of quite good articles, popular articles that we made this Quantum magazine, Wire magazine, which describe, this is very nice. Describe with some visuals, quite beautifully done. So, and if I may go back to your earlier question, what are the applications of this? Universality, right? That it's possible to turn one element into look like another element. So it turns out applications are quite broad and quite surprising. When I said that, we uncovered this, in reality, what we did is that the answer was this answer, in any text, basically almost in any textbooks on quantum, on any undergraduate textbook on quantum mechanics, you can find this answer. But people never thought about that, that formula in this new way. They never imagined that like a boring old like footnote which exists in every textbook of quantum mechanics could be turned into this powerful principle of new principle of optics. So it's when I'm saying this, it's kind of hilarious that it was just, this result was just waiting to be, it's just anybody could have picked up and just reinterpreted it.
I'm just not clear. So you're saying this makes elements look like other elements when they're not actually transmuted. Yeah, nucleuses aren't changed. But what is the use of doing this? Like, what are some of the commercial applications to driving substances like this?
Yeah, so let's go to applications. So applications there are several of them. First of all, you can, along as we discussed, as I described before, nonlinear optics, right, as a way to detect more accurately, and characterize substances. So you can use this fact to actually develop new protocols for doing this. First of all, you can try to improve accuracy of detection and optical discrimination for first application. That's the most straightforward. Second application, more interesting, is you can actually ask a question. Okay, so looking like is a property of light, right? Of how the light interacts. What about other properties of the material? Could this principle be extended to other properties of the material? In particular, for example, one of the questions that we are currently planning to study soon is, could you, for example, induce superconductivity using light for some boring materials? Could you take a boring material and shine a laser pulse and actually make this material superconducting? It is already known that for some materials, shining light on them actually can induce superconductivity. So this is, but it's already special materials. It's not boring materials, not everyday materials. It's all specially prepared materials. You shine with them with a simple light, sort of like weak light, and then it becomes superconducting. So we wanted to extend this perhaps to, more sort of make, you lose fancy light to make conventional materials exhibit this dynamic. And likewise, we can ask other material properties, whether it's possible to modulate them and at what will. So that's the second area. The third area, and this is we are actively right now studying, is we can actually revive the idea of using building computer based on light only. Surprisingly, this the principle of being able to make any element look alike is related to computing as a process. So we know, for example, that current computers are based on semiconductor technology, solid-state semiconductor technology. And current technology is very close to the physical limit of its limit. We cannot make transistors, smaller than 2 nanometers, basically. It becomes not a transistor, it becomes something else. Because new physical phenomena will take place. And so it's time to search for a new physical paradigm for computations. And quantum computing is one of the sort of attempt to find new physical paradigm of computing. So historically, light has been considered to be also as a physical medium for computation in early days. But of course, we only have computers based on electricity, right now. So this idea didn't work out. So why it didn't work out? It actually, roughly speaking, why it didn't work out this way is because, electrons, current is made of electrons, and electrons between themselves interact very strong, via, electrostatic force, and they repulse, and it's a very strong force. So it's very easy to make electrons interact. It's actually hard to make them not interact. And this is why it's easy to make transistors, such elements as a transistor, because transistor is actually highly nonlinear element, right? It's a highly nonlinear element in the sense that it has the digital structure. It has this discrete structure, right? So which means it's nonlinear automatically. With light, situation is very different. Light is made of photons. It's very, very, very hard to make photons interact. And this is why nonlinear optics kicked off only in 60s. After discovery of laser, because for the first time we could actually make photons interact between themselves. So it's very, very hard to make photons interact. And so people early days, when they tried to use light to build a computer, they actually tried to follow the paradigm of electronics computer, meaning you first make a transistor and then you integrate transistor into chips, right? Like this integrated scheme, integrated networks. So while it's possible to make, a transistor, all optical transistor where the inputs and outputs are all just light, the very fact that transistor, as I just said, is nonlinear element means it will operate only with a laser, very bright laser light. So it's also, which means that its efficiency is not going to be very high. So it's possible to make a single optical transistor. Now, integration of optical transistor into a network is basically, impossible due to the fact that their efficiency is very low. And so the very idea of following the paradigm of solid state computing, right, making, once again, the individual transistors and then integrate them into networks, just it's not a natural, it's not physically possible, it's not physically efficient way with doing with optics. So optics require, if you want to use light for information processing, it requires different way of thinking, very different way of thinking.
What's the trade-offs? Why use light to run a computer? Is it possible, on a level of millions or billions of transistors? Like what's the reason for all this?
Yeah, so there are two reasons. First reason is that heat generation in principle can much lower, would be possible to make it, heat. And, heat generation is a major issue, very major issue for performance of current computers. So the heat generation can suppress because light does not interact well, once again, with the matter, right? Not like electrons. And second is a more fundamental issue is that actually in principle, it's a speed. You would be doing information processing a little the speed of light, because light moves with the speed of light. So it's a possibility to reach the ultimate speed, physically accessible speed of information processing. And the third interesting thing is that light has a natural polarization built in, right? Because, for example, what is a white light? It's actually a collection of all the colors, or all the colors of rainbow, right? So they all together move. So in principle, like there is a parallelism in light built in, unlike a wire, right? You cannot move different currents through the same wire. It's going to be just one current, right? There's just no way, because current is just motion of electrons. But with light, you can put multiple colors into one optical fiber. Of course, it has to be an appropriate optical fiber, but nevertheless, it's possible. So parallelism is built in. Parallelism, bandwidth, speed, and low heat generation. That's a very, very important attractive feature of would-be optical computing. And so, if I may come back, so how our discovery actually is related to this aim of designing all optical computers. The idea is that, as I said, that we need to think about computation in a very different paradigm, just very different paradigm, and not just following the pattern of very successful pattern of solid state of microprocessors. And so for that, we need to step back and look, what is actually computer? What makes a computer? So a computer, obviously, it's actually, that Alan Turing is the one who told us what does it take to be a computer. So a computer has this universality property. It's called Turing universality. That's a machine that has it's a Turing universal machine. And what does universality means? I'm going to paraphrase it, for purpose of our discussion, and without going into computer science, is that it's a machine that can generate any possible output, assuming that you provide appropriate input. Let me just give an example. So when you use a laptop or any cell phone or any device, right? What you do is that you provide the input. You click, right? You click, you move, type, you move the mouse. That's all electronic inputs, in fact, right? Those are electronic inputs. Then this machine takes the electron and can actually produce any possible output. And the output will be like literally screen, right? What you see on the screen. So you can literally make any possible image on the screen, right? By just appropriately clicking, moving, and typing. Or, if you're computer science, if you're programming, it's probably more efficient just to write a program. So program is also an input into the machine, right? It's just different kind of input, but it is an input. So once again, a computer is a machine that can produce any possible output, provided that you supply correct input. Hey, but this is exactly what I just told about nonlinear optics. If you take any substance, you can actually make it produce any possible output with the right input. So there's an input that produces desired output. It's the same property. So nonlinear optics, nonlinear response, has actually the same fundamental properties as Turing completeness. So therefore, from this point of view, you should be able to build a computer, an optical computer, I mean, the fact that you can build an optical computer is not a new fact. But what's interesting is that what kind of substance is required to build this all optical computer? Or rather, what is the smallest possible computer from this paradigm? It turns out a single atom is enough. Because when I told you a substance, right, I did not specify how big or how small can it be. It actually can be as small as a single atom. So according to our insights, and recently actually published a preprint, actually literally called Single Atom Computing, it is possible. We showed how it is possible to build a computer on a single atom, one single atom, where the input would be just a laser light that interacts with the atom, and the output would be the light photons emitted by this atom. You collect them and you get the answer. And interestingly enough, to be able to program such a single atom computer, you would use some ideas from neuroscience, or like rather computational ideas inspired by neuroscience. It's actually called Reservoir Computing. It's sort of a version of neural networks, not a kind of deep neural networks, but a different version of it. And so this is the fact that such a universality in optics exists, once you start using a bright light, opens a way for rethinking computing and having it done on much more smaller scale. And this is by the way, it's also called neuromorphic computer for those listeners who actually might have heard about it.
But if you have a single is it a single transistor computer essentially, or when you say a single atom computer, how many states or how much information can a single atom hold? Even if it's 1 bit, you can harness them en masse. Would that be a lot more efficient and scalable and small than current computers?
No, I'm actually literally talking about a single atom, which means that in this paradigm of neuromorphic computer, you don't have transistors, right? This is what I was started with. I don't want transistors. Transistors are a problem for light.
But how much computing power can you get with one atom?
So it's in principle, as much as you wish. But trade-off, right? There is a cost to this. The trade-off is that the complexity in the brightness and bandwidth in the brightness of the incident light. The more you want to squeeze from a single atom, the more bright and the more bandwidth you need to have in the incident light, right? So there's a trade-off. And obviously this thing is, we are investigating this actively, so we don't have yet full picture. But there is this cost.
So, what is the ideal to have, if you can get things down to the single atom level, to have, let's say, a mole of atoms make a computer, or computers be made on the fly, or what are some of the possibilities?
Yeah, exactly. It's precisely this idea is to miniaturize, to be able to miniaturize further, to basically break fundamental barrier of current technology, right? To go beyond fundamental barriers of current technology, to enable to Moore's law to keep going, right? To keep moving. And that's, this is a very active research in general, right? New ways of doing computing, new physical platforms of doing computing. And as I just mentioned, quantum computing is one way, but there are many other computing paradigms, which, we don't hear as much as about quantum computing, but they exist, right? They exist and people work on them very actively. So this is just a contribution to that effort, right? So computational power, we need it. It needs to grow, right? We need to grow it. It's just the way the sort of modern society almost runs on it right now, and we need to, this is why it's important, this type of, we already see, we don't think about it, right, as a users of the internet and information technologies, but there is a cost, right? There's an energy cost to these things. And, thinking about paradigms also, it's about, new energy costs, reducing.
So what would this look like if it works in the future? What would a computer look like, or a handheld device look like, or how would it work differently if this is possible?
Presently, it's right. It's hard to imagine. We are talking about, we're only right now, in a way, if you will, writing grants to start doing actual, like a lab research on this topic, right? So what I have been telling you is a theory work only. So it's hard for me, and then I'm a theoretician, right? So it's hard for me to imagine the final device, right? But for now, it's a lab device, right? It's a huge lab, right? It's a big light it's a big lab with like big laser, but possibly even vacuum chamber, and big detector, right? So for now, we're talking about the very, very bulky things. It's not at all small, right? It's way bigger than anything.
But in the future, it's possible to have a computer that would be the size of a whole computer that would be the size of a postage stamp or less. Or how small could things get, you think? What form factors do you envision?
Yeah, so very good question. So in principle, I can tell you like the ultimate limit, right? Like ultimate physical limit. So it depends on the light you use, the frequency of light you use, or rather the wavelength of light, right? So light is a wave phenomenon, and the distance between nearest crests are the most important feature. So for example, green light is 600 nanometers, it's red light, but it's like 590. And 9 nanometers. So if you use like very, very blue light close to ultraviolet, right, on the edge of ultraviolet, but still visible, it's say 400 nanometers. So if you use 400 nanometer light as your input, right, and the computer cannot be smaller than the 400 nanometer, right? It has to be several, it has to be like say a factor of 10. So it's going to be like 4 micron large, right? At least minimum than this. So we talk about if ultimate limit, we talk about the micron size computer. That would be the ultimate physical limit.
Well, very good. Denys, what's the best way for people to find out more about your work and about this whole field of nonlinear optics? Where can they look? So
on my university's webpage or my bondar.tulane.edu, and there are references to a popular coverages, Quantum Magazine, Wire Magazine, and other professional writers explain these ideas much more better than I do, and with nice movies and pictures.
Yeah, well, that helps. No problem. Well, very good. Well, Denys, thank you for coming on the podcast. I appreciate it.
Thank you very much, and keep up this great work.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.